All right, ladies and gentlemen, if you want to twist timing in your favor, then you can take LSD or you can listen to Lisa Thalheim. Sorry. A warm welcome, please.
Okay. Can you hear me? No. Okay. Nobody can hear me? Can you hear me now? Still? More volume, more volume. Thanks. Is that better? Foo bar. Okay. Good afternoon. I'm going to talk about, well, the title is rather fancy, but it sounded better than talk on race conditions, but that's what the talk is about, race conditions. And I'm starting with a pretty picture from the 80s of a race condition, because it's one of my favorite movies. Other than that, it has no relevance to the talk whatsoever. I'd like to start with an I'd like to start with an opening note. I found just outside the knock, which greatly calmed me down. It says, "You're welcome to present abstract concepts to us," which is what I'm going to do today. I don't really know much about practical exploitation of race conditions, simply because I like to marvel at the shiny bugs I find and then get bored and move on. But there are people around who know about that, and you can make it your mission to track them down and ask them about actually tweaking load on a computer to get some obscure race condition exploit working. Okay, what I'm going to talk about is the mandatory intro. Then I'm going to introduce some common concurrency bugs, how to find and exploit them, and some not so common concurrency bugs, and close with some general advice when you're hunting for these kinds of bugs, and an end node. Okay, what are concurrency bugs? As the name suggests, it happens whenever there's multiple threads of execution happening, executing simultaneously, where threads, well, if you've done anything with threads, you're probably thinking about pthread, Win32 threads, but I'm in general talking about any string of code being executed in parallel, which can also include processes. So, what are the basic requirements that you need before you can even start looking for race conditions in the first place? Is that you need multiple threads of execution. So there have to be either really simultaneous execution of multiple threads, meaning multi-CPU, or simulated simultaneous execution, as in what you usually have on a one processor desktop machine, where the threads get scheduled one after another, but from inside the threads it looks as though they're... Oh, okay. Better? Great. I hope I didn't lose you. Yeah. That's better. So I was rambling on about multiple threads of execution, which can mean threads as in pthreads or Win32 threads, but also processes on different hosts. The next requirement is that they run simultaneously and share resources. So anyone who has brothers or sisters knows what I'm talking about when I use Lego bricks as scarce resources, or interact in any other way. For example, just communicate with one another using IPC mechanisms. So there's a whole host of concurrency bugs that can occur. Among them are deadlocks, live locks, mismatch communication, and false sharing, which I'm not going to talk about. It's simply because these are, first of all, quite rare to find in software because they're easy to find and easy to track down. If the software hangs, you can just attach a debugger and usually find out where exactly it hangs and what the bug is. And also, they're not very interesting for an attacker because usually when you hit a deadlock, that's basically the end of the line. So there's not much more in a deadlock than a denial of service, which is not all that interesting. Live locks and mismatch communication are the same. False sharing is just a performance issue. You can find more information on that in any operating system textbook. The interesting thing for an attacker are race conditions. So, what's the race condition? I think I'll start by showing an example. A really simple vanilla race condition, which may seem a bit cheesy because it's a constructed example, but I chose it for educational purposes. So, imagine you have a ring buffer sort of structure, and you have a store procedure, which always checks whether the limit of the ring buffer is reached, and if so, it just resets the ring buffer index to 0, and stores the data and increments the counter in a number of elements, which looks fair enough, I hope. So if you find mistakes in any of the code on the slides, that's very likely that there are actually mistakes. I tested the code, but you never know. So this code is okay in this setup. You have two threads, thread 1 and thread 2. And thread 1 comes in here, checks whether... So this, in the middle column, is the value of the RBF IDX counter. And imagine that it comes into this piece of code. The value of RBF IDX is 31. So it doesn't hit that piece of code, it just continues to write to the 31st cell of the ring buffer, increments it, at which point the index pointer becomes 32. And then the next thread comes in and sees that the RBF index pointer into the ring buffer is equal to cell, so it has reached its limit. So it resets the index pointer to 0 and continues from there. This is good. This is also still good. Thread 1 comes in as before, gets preempted at that point, meaning that it gets on a single core machine gets scheduled out and another thread gets scheduled in. And it sees that the RBF index counter has already hit the limit, resets it to 0, writes its data, everyone's happy. That at this point the structure is already inconsistent is a point, but never mind that now. So at this point the number of elements is not actually coherent anymore with a ring buffer. But it gets even more interesting if you have this kind of setup. The first thread comes in, checks whether the limit has been reached. Hasn't been reached, so this doesn't get executed. And at that point, it gets scheduled out for some reason. And another thread enters the same code, also sees that it still hasn't hit the limit, so this doesn't get executed, and stores its data into the 31st cell, increases the pointer to the next free cell, which is 32, which is beyond the limit, and at that point the thread 1 gets scheduled in again, gets to run again, and actually writes its data beyond the end of the buffer because the index pointer has been changed in between, but that thread has no means of knowing that. And it increases the index pointer once again, making 33, And because the programmer opted to check for equality here, this will never get hit again and will just run away forever. Or until it hits actually some crucial data of the process. So I showed that example because it's really easy to see how the order of execution of a series of statements can lead to a write beyond the buffer, which is a common concept in exploiting bugs. So that's just to set you up. And what we learned here is that the sequence in which code gets executed matters. And if you only have one thread of execution, it's given that code that is contained in the program serially will also get executed without interruption, without anybody altering the state of the world in between. But if you have multiple threads of execution that interfere or run in parallel, then you can have all kinds of, well, not quite foreseen events. And usually this results in data structures getting corrupted, which can, in this case, be used fairly straightforward to write beyond the end of a buffer. So if another thread comes in here, index pointer 33, this doesn't get hit, just writes happily beyond the end of the buffer, increments yet again and again and again. So this was a constructed example. I didn't actually find that in any software. It was just for showing you what I'm on about. And here I'd like to say some things about why I like race conditions. Race conditions are really hard to find. If you ask programmers, they will also tell you that they hate race conditions because they have a habit of showing up every 1,000 iterations and then never again. And then you just get random weird bugs and don't know what actually happened. And also race conditions tend to manifest themselves not in the places they actually happened, but somewhere entirely else on the code. And tracking down race conditions is incredibly hard and can be incredibly hard, which is why even if the programmer hits a race condition in his testing and debugging, there's a good chance that he'll never get around to actually tracking it down or fixing it, because it takes so much time and deadlines pressing. And also I like them because they're fun puzzles. Race conditions tend to be very complex bugs, and you have to keep a lot of context in mind to twist it around. So it's an intellectually interesting puzzle. You may have guessed by now that I'm more of a just give me some puzzle, I don't care about the implications sort of type. Okay, there are, race conditions can come in all kinds and forms, and we're actually going to see some that don't really fit into any pattern, but there are certain patterns when talking about race conditions. The first one is the forgotten lock, then we got file system races and signal races, and I'm going to talk about each of these in turn and give examples of them. Well, not for the forgotten lock, because the forgotten lock is just either the programmer didn't think of synchronization at all, or they used it inconsequently, which sucks because you just have to miss out on synchronization in one place in the code. You may do perfectly in all of your code and miss just one spot and one access to some global shared data, and then you're screwed, because then there's a chance that the data structure gets corrupt. So that's very much in favor of an attacker, because the programmer has to be perfect, and the attacker just has to find the one famous inconsequent use. And I'm thinking about whether I'm talking about that later.